In last class, we had discussed about the effect of windowing on spectral analysis using the DFT, and we had talked about two main concepts of spectral leakage and resolution. We said that the resolution corresponds to the width of the main lobe of a window, and the spectral leakage is directly proportional to the height of the side lobes. And we went through all the common windows, and at the end of the day, we said that the Kaiser window effectively helps us do the right trade-off between it helps us figure out what is the length of the window that we need and what parameters of the window we need if we are interested in a certain resolution and a certain spectral leakage. Okay, so today we'll try to finish off the discussion of Kaiser window. Kaiser window is given by, it doesn't have a closed form expression, it is given by this zeroth order modified Bessel function of the first kind, which you can't always compute. It has to be sometimes numerically computed, n minus alpha over alpha whole squared, 1/2 over I0 beta for 0 less than or equal to n less than or equal to m and 0 otherwise. So where the definition is that n, which is the length of the window, that is equal to m plus 1. Alpha is defined as m by 2. And this I0 is zeroth order modified Bessel function of the first kind, which comes from this solution of, so this zeroth order modified Bessel function of the first kind, this actually comes as a solution of this differential equation, this beta squared d2y by d beta squared plus beta dy over d beta plus beta squared minus alpha squared y equal to 0. If you solve this differential equation, the solution comes out to be this I0, which is called the Bessel function. You can write that I alpha beta, which is the alphath order modified Bessel function. So this is alphath order modified Bessel function of the first kind. So that can be given by summation m equal to 0 to infinity 1 over m factorial, this gamma function m plus alpha plus 1 times beta by 2 over 2m plus alpha. Now this gamma function is just a generalization of the factorial operation. So if alpha is an integer, then this gamma function is simply the factorial operation. Then gamma of m plus alpha plus 1 is equal to m plus alpha factorial. But in general, if gamma is not, if alpha is not an integer, if the argument of this gamma function is not an integer, then it is given by an integration. So gamma function is given by 0 to infinity t of x minus 1 e to the minus t dt. Okay, I'm just introducing some of these terms which you may find useful later. This thing called gamma function, which is a generalization of the factorial. You won't be asked to, for example, compute the modified Bessel function. These are solved through numerical methods, and you can fire up MATLAB, for example, And MATLAB has a command called Bessel-I, uh, alpha, beta, which helps you generate the modified Bessel function of alpha order modified Bessel function. In general, MATLAB also has a command for Kaiser window, so you can just use it simply as it is. So I just wanted to introduce you to where it arises from. But the Kaiser window effectively is given by two parameters. Um, the Kaiser window has one parameter being this beta. Okay, so this is one parameter, and the other parameter is of course this m, which is simply related to the length. So if you think about every other window, of course, that is described by one parameter, that parameter being the length of the window. You determine the length of the window, and it helps you figure out what will be the main lobe width and the peak side lobes. In the case of Kaiser window, you are given two parameters, and basically by adjusting them, you get a trade-off between the side lobe heights and the main lobe width. In general, the way it goes with Kaiser window is that if you increase your beta, okay, then your main lobe widens and your side lobe goes down. Okay. So if you fix the length of the window and if you just start increasing beta, what happens is that the main lobe keeps on getting fatter and fatter, but the side lobes keep on going down. Okay. And if you want to now decrease the main lobe, then what you have to do is you have to change the length of the window. So in general, this is true for all windows, not just Kaiser, which is that if you increase the length, which in the case of the Kaiser window, that is directly proportional to m, if you do that, then the only thing that it does is it reduces the width of the main lobe. So if you increase the length m, it reduces the width of the main lobe. But increasing the length never affects the side lobe height in terms of in dBs. In the dB scale, it never impacts the side lobe. Okay, so it does not affect side lobe attenuation relative to the main lobe height. Attenuation. So typically what you will be given is based upon your spectral analysis criteria. Someone will say, I want to achieve a certain side lobe height. I don't want the side lobe to be higher than this dB factor. And based upon that, and you are given that the main lobe width, so you want to resolve two frequencies which are so close to each other. And based upon that, you will pick your parameters m and beta. Okay. So a simple procedure will be that you are given ASL, which is the side lobe attenuation in dBs. And the second thing you are given is delta ML, width of the main lobe. So you can start by saying, well, the side lobe, since the side lobe is independent of the length of the window, right? The length of the window only affects the main lobe width, but it does not affect the side lobe. So the first thing you can do is figure out what is the right beta that helps you achieve that side lobe. Okay, and there is a Kaiser did this sort of rough calculation which lets us get close to the right value of beta up to a factor of 0.36 dBs. So if you are given ASL, you just use beta. You have this simple formula. One is, as long as your side lobe requirement is less than or equal to 13.26 dBs, you use 0, which is effectively using the rectangular window. Beta equal to 0 gives you the rectangular window. Okay. On the other hand, if your requirement is that the side lobe is 13.26 dB but less than or equal to 60 dBs, then you should really use this formula, 0.76609 ASL minus 13.26 to the power 0.4 plus, I'm going to go down, 0.09834 ASL minus 13.26. This formula is given as 10.13 equation in your text, just in case if you want to take a look at it in a better manner. And if you are given that the side lobe has to be bigger than 60 dB, as long as it is less than or equal to 120 dB, then you should use the value of beta as 0.12438 ASL plus 6.3. Okay. So if you use these formulas, it turns out that you can achieve the ASL factor. If you pick that value of beta, you come within 0.361 dBs of the actual side lobe. So you pick your beta, and then the next goal is you want to pick the value of M that gives you now the desired main lobe width. Now the main lobe width is going to depend upon both M, factor of M, and the beta that you have picked. Okay. So the formula that comes up is that approximately M that you should pick is equal to 24 pi ASL plus 12 over 155 delta of ML plus 1. Okay. So the effect of beta is coming in this side lobe factor here. So if you are given parameters, you just pick your beta, you pick your M, and you have a window which is going to satisfy those criterion up to some approximation errors. And then you simply take your signal and you window it with that signal, and then you compute your DFT. And if you do the right translation of your DFT coefficients to the DTFT and then the continuous frequencies, you have your spectral analysis working perfectly for you. Okay. So here are figures basically just showing Kaiser window, which is, this is of length 21. Kaiser windows, how they change as you go from beta equal to 0 and increase beta. And for beta equal to 0, Kaiser window is exactly the same as the rectangular window. Okay. As you go through different values of beta, you not only go through other windows, but sort of go in between all the other windows that we study. Okay. And as we discussed earlier, as you increase your value of beta, your side lobes go down and your main lobe width increases. So that's the effect, that for beta, your side lobe goes down and your main lobe widens. Okay. And then once you fix your beta, then you can simply now say, I want to increase my length. Now beta is fixed, you just increase your length, and then the only effect that length is going to have is it's going to bring this main lobe closer to 0. It's going to reduce the size of your main lobe, but the height of this peak side lobe, here, here, and here, it's going to be exactly the same. Okay? As you increase the length of your window, it's not going to change your side lobe height. If you remember these principles, you should have no trouble picking the right window, or at the very least picking the right length of the window to match the spectral resolution that you are after. So that is about all that we have to say about windowing. The basic message that you should keep in mind is that the moment you talk about using the DFT for spectral analysis, there are some effects related to leakage and spectral resolution that you encounter. The only way to avoid those effects is if you use windows of infinite length, which is never going to happen. Okay? And all that we have studied helps us figure out for a given length of signal what is the spectral resolution that we can expect. Now, another thing that we have to be careful about is how do we pick the length of the window, and then how many points of DFT samples do we need to take. So forth, what we are implicitly doing is that you get your, if you remember, what we were doing was we had a signal SC of t, okay, and we did anti-aliasing and continuous to discrete. I'm going to ignore the anti-aliasing to get xn. And then we said we'll window that wn to get some function vn, and we are going to now compute the DFT to get vk. And so forth, we have said, or being not very explicit about, what is the length of this window in relation to the number of points in here. So forth, we have used capital N for both of them. In reality, what you do is you pick Wn to be of length, let's say capital L, and then you use endpoint DFT so that N is greater than or equal to L. Okay? Because what is happening is the length L is playing a different role than the number of points of DFT that you are computing. What is the difference? Length L is helping you match Vn to Xn. The bigger length L is, the closer Vn is to Xn. Or, stated differently, the bigger the length of your window is, the closer the spectrum of your windowed sequence to the original sequence. Okay? So you want the length of the window to be bigger because you want the spectrum of Vn to look very similar to the spectrum of Xn. That is what the length of the window is doing. But what is the effect of saying, I want to compute endpoint DFT? Once you have a certain spectrum, what does DFT do? DFT is computing now samples of that spectrum. So the more spectral samples you have, the better sense you get of what the underlying DTFT look like. Okay. In particular, here is an extreme example of where L equals to N, and this is a signal which had two frequencies. Okay? So our Xn has two frequencies. But both the frequencies are multiples of my DFT samples. The places where I'm computing the DFT samples. So one frequency of Xn is omega naught equal to 2 pi by 16. which is equal to 2 pi over 64 into 4. So, and this is L equal to N equal to 64. Okay. So if my N equals to 64, I'm computing the frequency samples every 2 pi over 64 radians. So I'm dividing my 0 to 2 pi between 2 pi over 64 chunks. Now, I pick my omega 1 to be equal to 2 pi by 8 equals 2 pi by 64 into 8. Okay. So remember, what is windowing going to do? You have impulses at these locations in DTFT. And what does windowing do? It puts the spectrum of your window at those locations. Because windowing makes convolution of the spectrum of your signal with the window's spectrum. So if you do the convolution, what you get is this envelope. If you look at this envelope is the DTFT V of e to the j omega. Okay, this outer envelope that you see. This is the time domain signal, and this is its DTFT. Now, what is happening is that the zeros of this envelope are exactly at multiples of 2 pi over 64. Because our frequencies were multiples of 2 pi over 64, the zeros of these samples are also at multiples of 2 pi over 64. Okay. And what ends up happening is, if you now sample this envelope using the same number of points, using n equal to 64, which is the same as the length of the window, you end up getting this sequence. So you have just one non-zero here, you have one non-zero here corresponding to the negative frequencies, one non-zero here, one non-zero there, and you have zeros everywhere else. And you compute your DFT and you look at it and it has just two spikes and you say, oh, this is what my signal looks like. But in reality, what you're looking at is a wrong thing, because your spectrum that you sampled actually has this very non-negative structure. It is not zero everywhere. Okay? So the way to avoid that is that you increase your n, you make your n go much bigger than, so you make your n much bigger than L. For example, if you were to make your n equal to 128, what would happen? Now you will be sampling one additional sample between every 2 points. Okay? So you will be computing now a sample here. You will be computing a sample here. And all of a sudden, your DFT will start looking like the envelope that you started with. Okay? So it's important for you to keep in mind the distinction between what does the length of this Wn do versus what does the length of the DFT sequence that you are computing do. If your Wn is of a smaller length, you already have done the damage in terms of destroying the original spectrum. Whatever is the spectrum you are left with, you can only recover that now. But you can still use more samples of the DFT to at least figure out what is the spectrum that you are looking at now looks like. Okay? So there are two different parameters here. One is the length of the window, and the other is the number of DFT points. Here is another example of the same fact where you have you had a signal which was windowed using a Kaiser window. After windowing, this outer envelope is your V of e to the j omega absolute value. Okay, the length of the window is fixed now. You're not changing the length of the window. Okay. But you can still ask, what is the effect of taking more samples of the DFT? And the effect is that you are going to compute now more samples of the outer envelope. So in this case, we are computing n equal to 64 samples, even though the window is of length 32. And this corresponds to computing n equal to 128 samples of v of e to the j omega. Okay. So all that is happening is now between every two samples, what is the relationship between the two? Then now you are computing these additional samples in between the previous samples. Okay. So you now get a finer grid of the DTFT that you were sampling. Okay. So it's always a good idea to use bigger number of DFT points, but keeping in mind that as you increase your DFT points, that is not changing the outer envelope. Okay, this V of e to the j omega is not going to change by taking more DFT samples. Stated differently, if you lost two frequencies because they were too close to each other, and if you windowed them with a small length, you're not going to recover those lost frequencies just by computing more DFT points. However, you can get a better sense of what the spectrum, the underlying spectrum looks like, the spectrum of Vn, not of Xn, of Vn. Okay. So that's about as much as we have to say about spectral analysis using the DFT. You need to keep certain things in mind. What is windowing? What is the main effect of windowing? Spectral resolution, of course, leakage too. So those are the two main effects. How do you use different windows? Keep in mind Hamming being perhaps the right trade-off between your spectral resolution and your side lobes if you're really worried about leakage, and so forth. Now we want to move on from spectral analysis of signals to spectral analysis of time-varying signals. And for that, we'll be studying short-time Fourier transform, also known as time-dependent Fourier transform. And the goal here is we want to do spectral analysis of time-varying signals. So the motivation for that is if you look at a number of signals in real world, radar, sonar, speech, any other kind of data, financial data from stock markets, that data has a very time-varying nature to it. It doesn't stay the same all the time. Okay. And if you just do spectral analysis, all spectral analysis tells us is that these are the frequencies that are present in the signal. But it doesn't help us understand too well what is the underlying structure of the signal. For example, if you look at stock market data and there are some spikes in that data, well, you could say there are some frequencies, but when are those frequencies appearing? That time information is lost when you use DFT. So let's take a more concrete example to understand that better. So here is a signal which I am making as concatenation of three cosines of different frequencies. This is one cosine, and this goes on for 0.33 seconds. So this is a cosine of frequency 1 kilohertz. This is the other cosine of frequency 1.5 kilohertz, and this goes on for the next 0.33 seconds. And then finally there is this cosine which is of frequency 0.5 kilohertz. So this signal has a very time-varying nature to it. To begin, it starts with a frequency of 1 kilohertz. After 0.33 seconds, it changes into a signal of 1.5 kilohertz. Then it changes into a signal of 0.5 kilohertz. But if you were to do its DFT and do the right transformation, what will you get? You will get exactly the 3 frequencies that you started with, and you would have lost all the time information. So this is what you get if you do your spectral analysis using DFT. Right? You have these 3 frequencies sticking with positive, which is at 500 hertz, 1500 hertz, and 1000 hertz and 1500 hertz. Okay? And since they all 3 went on for 0.33 seconds, they have the same height. There's of course this leakage, spectral resolution and leakage effects that you see here. But they have exactly the same nature. And if I just show you this DFT plot, you cannot tell what was the nature of the signal. All you can say is, oh, maybe it consisted of 3 cosines. Maybe it consisted of sum of 3 cosines. But in reality, it didn't consist of sum of 3 cosines. It consisted of concatenation of 3 cosines. And that time information is what the short time Fourier transform tries to recover. So let's now take a more concrete example of time-varying frequencies. They are called chirps. Xc of t, which is cosine of theta of t, which is equal to cosine of, for example, some function. So your frequency is some function of t. Okay. And one case could be it is cosine of a naught t squared. So if you write it, this is like cosine of a naught t times t. So in general, when we write our cosine, we say whatever is being multiplied with t is my frequency. Now in this case, what we have getting multiplied with t, that is a function of time. So this is basically a frequency which changes over time. This particular type of signal is called a linear chirp because the frequency is linearly varying with time. There are of course quadratic chirps which are given by a naught t cubed. So you can write them as a naught t squared times t. So this is a quadratic chirp because your frequency is varying in a quadratic fashion with time. Okay. So this is quadratic change and this is linear change. Now in reality, the question is, what is really the frequency of this thing? What should be the frequency of this thing? And the answer is, it doesn't have one frequency, but you can talk about instantaneous frequency. And the way to talk about instantaneous frequency is that you simply say whatever is my d theta t, so you define your instantaneous frequency as d theta t over dt, which is the frequency at the instant of theta t. So in the case of the linear chirp, okay, the instantaneous frequency is what? It is 2 a naught t. So that is the frequency for a linear chirp. At time t equal to 0, it's 0. At time t equal to 1, it's 2 a naught, for example. For a quadratic chirp, the instantaneous frequency will be 3 a naught t squared. So you can talk about instantaneous frequency. And if you were to now do spectral analysis of this, and you have to really avoid the aliasing. So in this case, I have a sampling frequency of 8 kilohertz. Okay. And I am using this 500 hertz as my A naught. Okay. So my instantaneous frequency is what? My instantaneous frequency is 2 times 500 times t equal to 1000 t. Now if I measure this signal from t equal to 1 to t equal to 3 seconds, at t equal to 1 my frequency is 1 kilohertz, and at t equal to 3 my frequency is 3 kilohertz, and in between it's going to actually go through all possible frequencies between 1 kilohertz and 3 kilohertz. And because I end at 3 and my sampling frequency is 8 kilohertz, I'm not going to I will not be doing aliasing. So indeed, if you take this signal, as I have written, this linear chirp, and you do its spectral analysis, this is the plot you get. It says that your signal has a frequency from roughly 1 kilohertz to 3 kilohertz. And all the frequencies between 1 kilohertz and 3 kilohertz are present in the signal, which is true. But this spectral analysis alone is not telling you how did these frequencies come inside the signal. In fact, as time t goes on, it is never going to pass through the 1 kilohertz frequency again. In reality, what is happening is its frequency is growing linearly as time goes on. And that is what short-time Fourier transform helps you recover. So the formal definition of short-time Fourier transform is as follows. It is a function of, and when we are defining short-time Fourier transform, we are explicitly defining it for discrete sequences. Okay? It is a function of two variables. DFT is a function of one variable. It's a discrete sequence. Short-time Fourier transform is a function of two variables. Okay? It's a function of time and frequencies. So this is a discrete variable. And that is why you have this square brace. This lambda is your discrete frequency. If you prefer, you can stick with omega. And this is a continuous variable, so we use the parentheses to describe that variable. Okay, so this notation is sort of saying this parameter is discrete and the other parameter is continuous. So short-time Fourier transform is effectively, if you take away n, short-time Fourier transform is nothing but the discrete time Fourier transform. Okay, it's a generalization of the discrete time Fourier transform. And samples of the short-time Fourier transform help us do spectral analysis of time-varying signals, and we can get what is known as a spectrogram. So x and lambda, that is defined as summation m equals minus infinity to infinity x of n plus m w of m e to the minus j lambda m. This w of m, this is called, as the name implies, this is a window. So what is short-time Fourier transform doing? It is effectively doing a windowing of your time domain sequence and then computing its Fourier transform. Let's try to understand it a little better. Let's say that I were to write, and keep in mind that this, whether I use n or m, these things are just dummy variables, so I'll just do like this, m equal to minus infinity to infinity, x of n plus m e to the minus j lambda m. Okay. This n, think of it as a dummy variable, and this lambda as a dummy variable. Okay. If it makes you feel better, I'll write it like this. I will write it as n equal to minus infinity to infinity x of L plus n. So I'm replacing my m by n, and e to the minus j little omega n. What is this thing? What is xl plus n? That's just a left shifted version of my sequence. And what is xl plus n e to the minus j omega n summation n equal to minus infinity to infinity? That is just the discrete time Fourier transform of my left shifted sequence by L. So now let's get rid of these change of variable that we had. In fact, this is exactly the same thing too. This is DTFT of x shifted to left by an amount of m. So I could say that compute the DFT at time n equal to 0, compute the DTFT by shifting it by amount 0. At time n equal to 1, compute the DTFT by shifting it to the left by n equal to 1. So wherever I am in time, I just shift by that amount to the left. Or effectively, I make my origin, what is shifting by left? I'm making my origin as where I am currently in time. If I am at n equal to 10, I make my origin n equal to 10. And I just compute this DTFT. Okay. So now, instead of saying xn plus m, if you agree with that this is nothing but DTFT of x shifted to left by an amount of n, let's stick in the window that we have up there. Let's say now that we have m minus infinity to infinity x of n plus m, w of m e to the minus j lambda m. What is then now this thing? By the same token, this is simply the DTFT of x shifted to left by n times the window. Okay, so DTFT of x shifted by an amount of n times w of n. Okay. Just take a window and put it at 0 and multiply it with your shifted sequence and compute its DTFT. Okay. What effectively short-time Fourier transform is doing is it is going to different places in your signal one by one, and it is saying, just tell me what is the Fourier transform of this small region. What does that do? Because now you are asking a question about a very small region of your signal. If you take the example of the first example where I talked about concatenation of 3 signals. So I had 3 cosines at 1 by 3, 2 by 3 seconds. And this is 1 second. Okay. But short-time Fourier transform, if you were to design a window, you would basically just look at portions of the signal. You will first say, let's say your window is whatever in the number of samples. Let's say your window is of 1/3 second long in continuous time. Whatever is the number of samples. You first multiply your window from here to here and you compute the Fourier transform of this region. What will be the Fourier transform of this region? Just one sort of spike at the right frequency and nothing else. Now you shift your window a little bit, or effectively you shift your signal a little bit to the left, right? If you shift your signal a little bit to the left, your window is static. It's like you are looking through this window, your signal is shifting to the left. Now you are still looking at mostly the energy in your this frequency and a little bit of this other frequency. So you will still sort of see this one peak, and you keep on moving that. Eventually you will be like this. Okay? You will have shifted enough to the left that you will recover part of one frequency and part of other frequency, and now you will get two peaks. But the height of those two peaks will be smaller than the height of this one peak, because you are getting, first you are getting samples of one frequency for 0.33 seconds. Now you are getting samples of one frequency for 0.3 divided by 2, the other frequency for 0.3 divided by 2. And once you move completely, you shift your signal so much that you are only covering the second frequency, you again just see one peak. Okay? So if you were to compute this discrete time Fourier transform as a function of n, and you were to plot that for different values of n, typically so you will get a 3D plot. For example, you could have n here, and you can have your frequencies lambda here. Okay. For the first few samples, you will get a peak at one frequency. Okay. You'll sort of get a peak around this region. So this is 3D. This is supposed to sort of pop out of the screen. Okay. And then after a while, you will also start getting, when you are halfway through, you will start getting the other frequency, a little bit of the other frequency. And then once you cross the threshold, you get a really thick this part of the frequency. Okay. But a little bit of this frequency will still come in. It will sort of bleed in. And for another, you go through for, this is for 1/3 second, another 1/3 second, and the same thing will happen for the next part, and this keeps on going. So you get these three-dimensional plots, which are called spectrograms. So this is a pictorial representation of what short-time Fourier transform is doing to your signal. This is a linear chirp. As you can see that it starts off at a lower frequency and then the signal's frequency is increasing. Okay. What the short-time Fourier transform does is for every value of little n, so this is n equal to 320. So it has moved its signal to the left that effectively you are starting at 320th sample as your origin. And then you multiply that with a window. This is a Hamming window. So you multiply your now shifted sequence by a Hamming window, and then you compute the Fourier transform of that portion. And because your portion only includes this region, it is going to report frequencies that are contained in this region of the linear chirp and not all the frequencies that existed earlier, that exist beyond that region. Now, if you go to n equal to, for example, 720, which doesn't overlap with this 320 at all, Now you have gone to higher frequencies. So you have now shifted your signal. Now your N is 720. So you now go to these higher frequencies, and again you multiply it with this Hamming window, and you now compute the Fourier transform of this region. And you will again get some frequencies that are contained in this, but not all the frequencies like we saw in the example. In our example, for example, we were seeing all frequencies from 1 kilohertz to 3 kilohertz because we were not doing that windowing operation that is integral to the short time Fourier transform. Here is now a more explicit thing. This is again a linear chirp. So the discrete sample, the linear chirp in discrete time is a linear chirp. The sample of a continuous time linear chirp is a discrete time linear chirp. So if you were to just compute the DTFT of this thing, okay, you have 20,000 samples of the signal. If you were to compute just the DTFT of this signal, this is what you get. You see all frequencies from almost starting at n equal to 0. Right? What is the instantaneous frequency of this thing? This is 2 alpha naught n. That's the instantaneous frequency of this chirp. So you are going to compute DTFT of the whole signal, and you look at it, and you see that you have frequencies everywhere from 0 radians to 0.3 radians. Now you could do the short time Fourier transform, which is effectively just shifting your signal by different amounts. So this is the short time Fourier transform, which is it looks at this thing. It shifts your signal by the amount, by the index that you are interested in calculating. So this is n equal to 5,000. Multiplies it with the window. In this case, the window is a Hamming window of length 401. And then asks, let's compute the Fourier transform, the discrete time Fourier transform of that region. That region is now of length only 401. So this is x, this is the short time Fourier transform, capital X, 5,000 lambda. Okay. And if you do that, you see that at that time, you have some frequencies are between 0.1 and 0.05, okay, but nothing anywhere else. Why? Because you windowed it, so the short time Fourier transform is not now considering frequencies that existed at other times. Okay. And if you go down and now you compute, for example, x 15,000 lambda, then you get this. Okay. So around n equal to 15,000, your signal consists of mostly frequencies between 0.2 and 0.25. And you can make this time-dependent conclusion about your signal. Rather than saying, oh, my signal consists of all frequencies between 0 and 0.3, you can now make this time variant frequency decision. My signal at this time had these many frequencies. My signal at n equal to 5,000 had these frequencies. And it had no frequencies, for example, close to 0 or close to 0.3. At n equal to 15,000, my signal had frequencies which were between 0.2 and 0.25, and it had no other frequencies. Okay. That's what the short time Fourier transform helps us accomplish. We'll come back to this example in a different context, but I just want to give you a sense of what do short time Fourier transform plots look like. As we talked about, they are really 3D plots. Okay? You are asking the questions, at this time, what are the frequencies in my signal. So this is an example of that short time Fourier transform plot, which is on the x-axis you have the time n, and you can translate, if you are given a continuous time signal, you can translate that into continuous time too. And on the y-axis, you have the frequencies normalized by 2 pi, so between 0 and 0.5. And again, if you know the sampling frequency, then you can translate it into continuous frequencies. So what this says is, and I don't have to give you the question, what this says is that your signal consists of not sum. It consists of concatenation of three signals. Okay, it has three distinct plots effectively. This plot corresponds to, this is a plot of a linear chirp. It says that at time 0, I have a small frequency. As my time increases, my frequency is increasing. That is just the plot of a linear chirp. At this time, I have frequencies that are given by the cross section. If I take a cross section like this is giving me the frequencies that are present at that point. So this is a linear chirp. And then it stops here. What does that mean? That my signal at sample 20,000 stops having linear chirp within itself. Instead, it now has, so what is this straight line saying? This straight line is just a pure sinusoid, one frequency. So after n equal to 20,000, my signal stops having chirp, and instead it has now one, maybe cosine or sine. We'll have to look at that, but if you are just looking at the magnitude, one frequency. And then at n equal to 25,000, all of a sudden another frequency has appeared. It's again a straight line. Okay? And so you can now effectively write down equations for this system, that for first 20,000 samples I had this signal, then for next 5,000 samples I had this signal, and for next 5,000 samples I had sum of two sinusoids, which is something that a discrete Fourier transform based spectral analysis cannot give. If you had a quadratic chirp, for example, that chirp will look like just a quadratic function of frequency. It will go like this. Okay, with time, the frequency is growing quadratically with your time. Okay, you can think about polynomial chirps, and they will make sort of these weird, you can have chirps like this, which will be polynomial functions. Whatever it is, the short time Fourier transform up to certain trade-offs will capture those effects. Okay, so it's a really powerful tool for spectral analysis of dynamic signals. So we want to say a few things about the invertibility of the short time Fourier transform. And the short time Fourier transform, as we talked about, is simply the discrete time Fourier transform of xn plus m w of m. So the short time Fourier transform at time n is simply this windowed version of my signal and the DTFT of that. Okay. So since the DTFT is invertible, this means that the short time Fourier transform is invertible. In particular, if we are given xn, so if we are given xn and we know its Fourier transform, we can compute xn using the inverse Fourier transform formula. So now we are given that xn plus 1 has the DTFT given by xn lambda. So we are given this relation that xn plus m Wm has the DTFT given by xn lambda. If that is the case, then we can simply use the inverse DFT formula to compute xn plus m. So we can say xn plus m Wm is equal to 1 over 2 pi minus pi to pi x of n lambda e to the j lambda m d lambda. So if I want to now compute xn plus m, I can simply divide by Wm now this is true, so I can divide by Wm as long as Wm is not equal to 0. So the short time Fourier transform is invertible as long as my window has at least one non-zero sample. Okay. Short time Fourier transform is invertible as long as Wm is not all zeros. If it's just one sample which is non-zero, we always divide by Wm, we get xn plus m. So for some other value of n, we get another xn plus m, and we keep on doing that for different n's, and we recover our whole signal. Okay? So short time Fourier transform is simply invertible using just the knowledge of discrete time Fourier transform invertibility. The main thing though is short time Fourier transform is not an orthogonal transform. Okay, short time Fourier transform is not an orthogonal transform. Now, if you think about the short time Fourier transform, so far we are simply saying short time Fourier transform is a function of little n and continuous frequencies lambda. We haven't talked about computing the frequencies. Okay? But doing that is not that difficult. We can simply use the DFT to sample the frequencies. In general, short time Fourier transform is continuous function of lambda, just like discrete time Fourier transform. But short time Fourier transform, we can sample the short time Fourier transform in the lambda domain using DFT and compute it. We'll come to that later. I just want to briefly say the effect of windowing. Even though the windowing that we are doing in here is for a different purpose than the windowing that we do in the case of spectral analysis using DFT, the effect is very similar, and it gives rise to a trade-off between time resolution and frequency resolution. So let's look at what is the effect of windowing in the short time Fourier transform. What is it that is giving us the time resolution? Think about it. In the normal spectral analysis, we wanted large windows because large windows mean shorter shorter main lobes, right? Or not that fat main lobes. Now, what happens in the case of short time Fourier transform? So let's look at example of this chirp sequence. I'm trying to make it a chirp, but so the idea in short time Fourier transform is you shift it and then you window it by some length. Okay, so you can talk about Wm being of finite length say Wm equals to 0 for all m naught in 0, 1 up to L minus 1. So we have still a window of length L. Okay. Now, if my window length, so let's say if my window length was up to here, if this was my L, I'm computing now the the Fourier transform of this region. Okay. Now let's say I increase the length of my window. I say now my length of the window is this. Okay. This is L prime, and now I'm computing the Fourier transform of this region. What is going to be the effect of the two windows in this example? Assume that this is a linear chirp. Okay. As I increase the length of my window, so we saw earlier that if we compute the Fourier transform of this small region, we get a small sort of hump which is centered around the frequencies that are contained in this part of the signal. So this will be this, right? Now, for this longer version, okay, what is going to happen? If I am now computing a longer window, I'll have more frequencies within the same portion of the signal. Okay, so I am going to, for the same portion of the signal, I'll actually get a little thicker version. Okay, so the length of the window in here actually forces you to have lower time resolution. In reality, some of these frequencies, if you increase the length of the window, some of these frequencies were actually only appearing later in time. But because you made your window long, what happened? Because you made your window long, you are now looking at frequencies that are far ahead in the signal. So you're getting more frequencies, which means you can't distinguish when they started in time. Okay? So having a larger window having a longer window reduces time resolution. And by time resolution, I mean you can't say when does a frequency start and when does a frequency end. So if you look at your spectrogram, for example, and let's say you had two frequencies, having a very long window, you may get something like this. Okay. Even let's say your frequencies were divided here. Up to this point, you had one frequency. Up to this point, you had one frequency. Up to this point, another point, you had another frequency. So this is n and this is lambda. Okay. But having a longer window is going to cause you to include samples from the other frequency for a long amount of time. And what would happen is that if you look at your spectrogram, you can't really do a good job of distinguishing when does one frequency end and when does the other frequency start. Okay, you get poor time resolution. At the same time, because your window was large, and if you go back to your spectral analysis, because your window was large, you are actually getting really good frequency resolution. If there was another frequency very close to this, if there was another frequency, if there were two frequencies, if there were two frequencies very close to each other, okay, because you are looking at them for a longer duration, you can tell them apart. So having a longer window, we know helps us distinguish between frequencies, but having a longer window also does not let us distinguish easily in time. On the flip side, if you want to really tell when does a frequency end and when does another frequency start, you want a smaller window. But what is the effect of that smaller window? It gives you really good time resolution, but you now lose the ability to distinguish in frequency. You have the same effects of having leakage in frequency and loss of resolution in frequency. So having a longer window reduces time resolution but increases frequency resolution, and vice versa. So there is this fundamental trade-off, the time frequency. You have this time frequency trade-off when you are analyzing signals for time and frequency. You can't achieve, it's sort of the Heisenberg uncertainty principle. You can't simultaneously achieve good time resolution and good frequency resolution. Okay. So coming back to this example, here is the case where we have a longer window, and below we are plotting for the case where we have a smaller window. Okay. If you look, because you have longer window, you are able to distinguish between these two frequencies very easily. They are very close to each other, but you are able to distinguish between them. Similarly, the width of, look at this chirp, the width of this chirp is not that big. Okay? You can see that it's probably one chirp and not multiple chirps aligned with each other. Okay? But now let's reduce the length of the window. If you reduce the length of the window, then you will have a really easy time telling where things started and stopped. Because if you look here, because of a longer window, even though the transition between the two signals was abrupt, one stopped and one started, you can't see that from this picture. It lingers for a while, this thing and this thing, there is certain overlap because of the length of the window. Okay? But now, reduce the length of the window and see what happens. This width of this in time has shrunk because now I'm overlapping less and less of samples from other part of the signal. So I can immediately tell, oh, this is where. If you look at it now, you can at some level say that at exactly n equal to 20,000 samples, my chirps ended and this frequency started. And similarly, you could come here and say at exactly 25,000, one thing ended and the other is starting. But what is the effect of that in frequency? You have the two frequencies merged together. You have bad frequency resolution. Because of the same effect that we did earlier, due to windowing is going to cause convolution with the Fourier transform of your signal, and that is in turn going to make your frequency into these wide lobes. So smaller window, wider main lobe, and that's going to, you are going to lose your spectral resolution. Similarly, if you look at this chirp has thickened. So now you can't tell actually it was just one chirp or maybe there were two chirps very close to each other. You don't know. Right? So there's this fundamental trade-off between time resolution and frequency resolution. You can improve one, but at the expense of the other. We'll end here, and then we'll try to finish it off by discussing computation of the short-time Fourier transform using DFT.